We're going to briefly talk about hemiacetals, acetals, and chiral molecules. Now, this is the precursor to carbohydrates. So this is going to wrap up what's on exam 2 and will hopefully prepare us to start talking about carbohydrates. So I want to go over a definition of hemiacetals and acetals. I know this can be a little bit of a strange concept, but a hemiacetal is a carbon atoms that contain a hydroxyl group, they have to contain an OH, and an alkyl oxy group, which is the OR. So an oxygen attached to some other carbon-based group, like we saw in ethers. So this could be a methyl or an ethyl or a propyl. Now they're formed when an alcohol adds to an aldehyde or a ketone, and there's in the presence of an acid catalyst. So we have an aldehyde or a ketone, and we add an alcohol, and we're going to make what we call a hemiacetal. Now what happens is that we're going to react, if we want to take the hemiacetal, we can potentially react that with another alcohol, and we can form an acetal. So an acetal is a carbon atoms that contain what we call two alkyl oxy groups. They contain two OR groups. So it's going to go COCOC is the pattern we're going to see. And an acetal forms between a hemiacetal and an alcohol. And these are realistically what we're going to start talking about and calling our sugars and our carbohydrates, our simple sugars. So acetals that form from aldehydes are when we see an aldehyde mixed with an alcohol, and we form what we call a hemiacetal here. If we take that hemiacetal and react it with another alcohol, we're going to form an acetal. And this is that alcohol group attached to that what we call alkyl oxy. So we have that COCOH is a hemiacetal, and the pattern of an acetal is that COCOC. Okay, the two alkyl oxy groups. So I want you to feel comfortable in just identifying a hemiacetal versus an acetal. Don't get caught in the weeds here, okay? So acetals from ketones, in this case, we can take a ketone. These are a little less reactive than aldehydes, but we can add them to an alcohol, react them under acidic conditions, and we can produce a hemiacetal. But in this case, the hemiacetal right here, we have our alkyl oxy group attached to our OH, okay? So we form a hemiacetal from the ketone. Now we can react that with another alcohol, and we can form an acetal. There's that COCOC bond, acetal, okay? Now, all of our glucose molecules, and actually our simple sugars, are hemiacetals. They're either hemiacetals that were made with aldehydes or with ketones. So if we look at glucose itself, glucose C6H12O6, it has a structure that looks like this. It's called a Fischer projection because it's written up and down. We have the aldehyde at the top, and again, because we have an aldehyde, remember this is what's going to be considered carbon 1 when we start numbering our carbons, okay? And we have all these adjacent OH groups. So here we have our glucose molecule. When glucose is in its cyclic form, so this is straight chain, this would be cyclic. Cyclic means it's connected together, okay? This is the straight chain forming into the cyclic form. But when glucose is in its cyclic form, like we normally find in the body, it's considered a hemiacetal because we have what we call an alkyl oxy group, okay? So here we have that COC, so we have that bond, our alkyl oxy, attached to an OH. So we become a cyclic hemiacetal. So I just want you to be able to just tell me these things here and be able to kind of produce this on an exam. If you can understand this learning check, then you'll be okay for what's on exam 2. I just want you to be able to identify whether this is an acetal or a hemiacetal. So since we have one alkyl oxy, COC bond, and an OH, this is considered a hemiacetal. If we're looking at B, we have that pattern COCOC. So we have two alkyl oxy groups. This one is considered to be an acetal. So hemiacetal and acetal. So when we talk about cyclic acetals, we can add an alcohol to a hemiacetal and we can form an acetal, a cyclic acetal. And what's really interesting and what I would like you to know is bolded in red is that the bonds, when we start bonding glucose molecules together and forming disaccharides or polysaccharides, that bond that holds, that glycosidic bond that holds those glucoses together is actually an acetal. So it's an acetal bond that will hold disaccharides and polysaccharides together. So it's this type of bond that we're going to see in carbohydrates. So it's very important in carbohydrate chemistry, and we'll kind of get into it later on when we start talking about carbohydrates. So if I show you a simplest disaccharide that we can form, which is maltose, it's two glucoses added together. We actually can see here's our glucose molecule and our glucose molecule. We've attached them together. And it's this bond that is a cyclic acetal bond. So here we have the alkyl oxy group, our COCOC bond. Here is the acetal bond. And on one end, we're going to retain what we call the hemiacetal, that's COCOH, okay? So disaccharides are linked by acetal bonds. And this is kind of just where we're getting into that pattern and understanding the difference between a hemiacetal and an acetal. And when we have any of our carbohydrates in cyclic form, they'll always have what we call a hemiacetal end. Now, I also want to get into the idea of stereoisomers. So we can have things that are called structural isomers, where they have the same formula in different bonding arrangements, like what we talked about with butanol and when we made that methylpropanol, or here just ethanol and dimethyl ether. It's the same number of carbons, hydrogens, and oxygens, but they're arranged in two different arrangements to make two completely different molecules. A stereoisomer, on the other hand, is one that is bonded in the same sequence, but it has a different arrangement because they're non-superimposable mirror images. So I'd kind of like you to, I would like you to know the definition of a stereoisomer. So they're bonded in the same sequence, but they're non-superimposable. And this is where we got into the idea of when we were talking about pheromones and hormones, and they would look similar but different, and how they'd have the same arrangement but on different sides. It's the same idea here. We talked about a stereoisomer. That's the cis and trans. So cis and trans stereoisomers are the same thing. So you already kind of learned it. We're just going to apply it now to a different thing. And here, when we start talking about chirality, this is important because this is how we can get to identifying those enantiomers and stereoisomers. We need to know whether a molecule is considered chiral or achiral. So if something is chiral, you can't superimpose it on itself. So an example is your hands. Your hands have the same number of fingers, okay, and same arrangement. So if I show you my hand briefly, if I can open this up, try to get my window open. So your hand has the same arrangement. It goes from your thumb to then your index, middle, ring, pinky. Now, on the other hand, I cannot put one hand on top of the other, non-superimposable. I still have the same arrangement, thumb, index, middle, ring, pinky, but in this case, they don't superimpose. You can't put them on each other, okay? That's what we mean by chirality, okay? Same arrangement, but you can't superimpose them. Now, achiral is when there's something that's very identical and you can superimpose it. So just to give you some real life examples, we're going to go over here. So your hands are not superimposable. These are chiral. So a pair of gloves, even sneakers. Sneakers are identical in how they're made. However, your left sneaker does not fit on your right foot. And your right sneaker does not fit on your left foot. But if we looked at a glass or a baseball bat, those are considered achiral because they're identical and the same. So what it means to be chiral is actually really simple. In chiral, it just means that you have a carbon with 4 different atoms or groups attached to it. So if we look at that carbon in the center, so here's my carbon. I'm going to draw them right here. To be chiral just means that you have 4 different things. These groups that are attached here have to be different. One could be a hydrogen, one could be a methyl, one could be a Cl, and say the other is a Br. As long as these 4 groups are different, this is considered chiral. Okay. If I have 2 that are the same and say this turned into a hydrogen now, this would no longer be chiral. It would be considered achiral. So we need 4 different groups to be considered chiral. The other word I would like you to know is an enantiomer. And an enantiomer is a stereoisomer that we cannot superimpose. It's like the same word as a stereoisomer. These are just kind of showing you images, how we can't superimpose them. So if you have 4 different groups, then you are considered chiral. If you have 2 of the same groups, then you could eventually superimpose them. So when we start talking about chiral and achiral and stereoisomers, this is where we're almost getting similar to cis and trans, like we had discussed before. There's different biological effects that you'll see. So if we look at spearmint and caraway, completely different flavors. So spearmint obviously is a minty flavor. Caraway is a very licorice flavor and intense. They have the identical molecules, except that one is in what we call an L arrangement and one is in a D. So they cannot be superimposed, but their sequences and their components are the same, okay, but completely act differently in the body. So if you can understand this and tell me if these are chiral or achiral, you're doing good. So here's that carbon. We have 4 different groups attached. This chiral is considered, or this carbon is considered chiral. I gave you the answer, whoops. In this case, again, 1, 2, 3, 4 different groups. This carbon is chiral. Here we have identical groups. So this is achiral or not chiral. Now, when we draw some of our molecules, sometimes we've seen and we've drawn our straight chains going across. Now, when we start drawing our carbohydrates soon, we're going to draw them in what we call Fischer projection, which means that we're going to draw them going up and down, okay? Instead of right to left, now they're going to go up and down. It's a 2-dimensional representation of the molecule. And what we do is we place the most oxidized group at the top. So you'll always see an aldehyde at the top, or you might see the ketone towards the top. The other thing is that we're going to use vertical lines for bonds that go back and forth, and horizontal lines are bonds that go forward. So here's our Fischer projection. You don't have to worry too much, but they go up and down, okay? And our aldehydes are going to be at the top because they're the most oxidized, the highly oxidized group. And then on the sides, you have these hydrogens and oxygens, well, our hydroxyl groups, OH. Now, what we can do is if we have a compound with 2 or more chiral carbons, so these 2 in the center technically are considered chiral. That means that we can designate them and designate an isomer in an L or D arrangement, depending on where this OH group is. So the way we can determine if we're chiral, remember we have to have 4 separate groups. So in this case, this one up top, the aldehyde cannot be considered a chiral compound because it has a double bond. We need 4 separate groups. If we're looking at this carbon in the center here, okay, right up top, we have one group that's an OH, one group that is this aldehyde, one group that's a hydrogen, and this, all of this compound down here, the rest of it is the other group. Because these are four separate things, this carbon is chiral. If we go down to the next carbon, again, one is an OH, one group is a hydrogen, one group is all of this up here, and another group is all of this down here. Because these are four different groups, this carbon is chiral. If we look at this last carbon, this one is not capable of being chiral because it has two hydrogens. And if we have two of the same thing, two similar groups, we are considered achiral. So typically in Fischer projections, your first and last carbons are never chiral, but everything in the middle is. And if we at least have two or more in the middle, we can be in an L or D arrangement. And if the last OH group above the final carbon, so if we go to the last chiral carbon, if the OH group on that chiral carbon is on the left-hand side, it's an L isomer. If it's on the right-hand side, it's D. So we're going to go over a few examples and then we're almost done. So the first one I want you to tell me can these be superimposed? So are they considered chiral or not? The first one here, four different groups. So these two are chiral and they cannot be superimposed. These, however, have identical groups. So these are considered achiral and they can be superimposed. Now, if we look at this molecule here we have what's going to be considered an aldose later on that you'll learn about. The top is not chiral, the bottom is not chiral, but I have all of these in the middle are chiral compounds. I want to know if it's in the L or D arrangement, so I go to the last chiral carbon. I look at the OH group, and if it's on the right, it is D. If it's on the left, it's an L. Because this is on the right-hand side, this is considered a D isomer. So that's basically it. We kind of wrapped up and really gave you a precursor to what we're going to talk about in carbohydrates. So this concludes everything that will be on exam 2, and we're going to get back at it when we start talking about carbohydrates next week. If you have any questions whatsoever, please let me know.